Hello, good morning to everybody. I'm Pere Malgrat. Nowadays I'm the head of Urban Space Department of Barcelona City Council. My 35 years of professional experience have been dedicated to advanced planning, project construction, management, operation, and maintenance of urban drainage system and other urban services. It's really a pleasure for me to chair this session because, in fact, I have been the coordinator of RESCCUE project during 2.5 years of the project before my present work at Barcelona City Council. In fact, 3 of the 4 sessions that we're going to see are related to RESCCUE project. So are my all partner and friends that will be here to present the main works nowadays at the end of the project. No? This session is about climate impact assessment, which it's a very interesting issue. Nowadays is one of the issues that you can find more in the media and the policies and so on. No? I would like to remark that in order to have a complete and accurate assessment of climate impacts, a risk assessment should consider both tangible and intangible impacts related to extreme events, as well as direct and also indirect damages. Traditionally, people work more than direct, but increasingly people are going to work more with indirect damages that are induced by direct impacts and may occur in a space or time outside the event. These sessions, we're going to see 4 cutting-edge methodologies to perform comprehensive climate-related risk assessment and implementation in real case with different scale. The first presentation will be made by Alistair Ford. Dr. Alistair Ford is a lecturer in the School of Engineering at Newcastle University. He has over 50 years experience of developing urban models to assess the impacts of climate change, particularly extreme weather events such as pluvial floodings. We are going to see a presentation with an issue that, in fact, is very interesting for me for my present work. That is, the title is, Can we quantify indirect economic impacts from pluvial flooding? A case study on transport in London. Please, Alistair, is your time.
Thank you, Pere. Hopefully you can all see my screen now. So this is some work that was done actually in another EU project called RAMSES that finished a few years ago and was undertaken by Dr. Maria Pregnolato, who's at Bristol University, and Professor Richard Dawson at Newcastle, and myself, Alistair Ford. So the context of this is that we often hear about the economic impacts of things like extreme weather events, particularly flooding in the UK. And as Pere says, it's important to think about tangible, intangible, and direct and indirect impacts. Quite often these economic estimations of costs have little in terms of methodologies described, and we often don't understand how they've been quantified. A lot of the time they come from insurance companies, but we know that there are much wider costs and damages in urban systems that we need to take into account. So these impacts of extreme weather events, like the ones in the previous slide, are difficult to quantify, and things like heavy rainfall, which leads to pluvial flooding, have the potential to disrupt transport networks in cities. We know that the impacts occur both at the location where the climate threat is experienced, so where the flood hazard appears in the urban system, but also in much more remote locations because of interdependent networks which can transport that impact further afield in the urban system. So what we also want to understand is that analysis of indirect impacts is key to assess, truly assess climate impacts from these kinds of extreme weather events and identify the cost-effective adaptation measures that we might put in place to protect urban areas. So we focused on urban transport networks. Urban transport networks are vital components in these urban systems. They underpin the urban economy and the social systems in cities, and they're also vital for emergency response during disasters. Disruption to these transport systems from things like extreme weather events impose costs on the urban economy, but the quantification of these costs and measurement of the size of that disruption and the economic impact is not straightforward. So here's an example of a rainfall event in Newcastle a few years ago, and here's some work that Maria Pregnolato did looking at quantifying the impact of that event on traffic flows on the road network in the city. So we could see a drop in the traffic flows from the normal levels that we see during the rush hour. But what does that drop in traffic flows cost? Does it cost the people who are traveling? Does it cost businesses? How do we quantify that? That's what we want to do this work to understand. So we try and follow this process of going from global to local to a hazard using a series of downscaled models. So we downscale from global models to local meteorology models, and we use high resolution models of rainfall, which then go into high resolution models of hazard, in this case our CityCat model at Newcastle University, surface water flood model, which includes urban drainage. And then we want to quantify the impact. So in this case, the impact might be some disruption to the urban transport network. Here are some locations of flooding in the city system. And importantly, then we want to think about what the response might be to reduce that impact in the future. So by doing that downscaling approach, we can produce simulations like this. So this is a simulation of all of Greater London for a given rainfall event. This is a 1 in 200 year event that shows the surface water depth resulting from the rain falling across this area. Now we assume in this case uniform rainfall across the whole area, which is obviously very large, but we can also simulate rainstorms moving through the urban system. And what we end up with is on the right here, a depth map where we understand the depth of water at every pixel, and we can overlay that onto the road system to understand the depth of water at a given point along the road network resulting from this rainfall event. We know that road system is used by many facets of the urban economy. And I should say, actually, we've also simulated the railway system too. So it's not just the road network, it's transport networks in general. So if we look at London's urban economy, this is Greater London again, and here is the percentage of London's jobs in the finance sector across Greater London. And there are two main hotspots, the City of London in the centre and the Canary Wharf area over here to the east. Now we know that the people who work in those jobs and produce the economic activity don't necessarily live in the same zones. So if we map out for example, the City of London, this central orange one here, the journey to work flows that feed that location, we can see these travel from a much wider area across the southeast of England, much greater than Greater London. And the thickness of the line here shows how many people are traveling in. So there's several hundreds of thousands of people traveling into that area every day on their commutes to travel and produce economic activity. And those people rely on the road network and the public transport networks to travel into the city. So this is a network model that we've built that integrates all of the public transport modes together into integrated transport network, which we can then use to analyze the impact of those flood events on the network. Now, how do we do that? Well, we use, again, this is some work that Maria Pregnolato undertook a few years ago, producing a depth damage function, or a depth disruption function, I should say, where we can, for a given depth of floodwater on a transport link, in this case on a road link, we can assess the reduction in performance of that transport link in terms of the speed that traffic can travel at on that road. So this links floodwater depth to vehicle speed, and then we can reassess the travel times across the network in that way. We can also do the same thing with the railway lines. Once the floodwater depths reach a certain level, speed restrictions are imposed on railway systems, and then we can assess how much delay that causes to those journeys that I showed on a previous slide. And what we can do then is aggregate up all those journeys. We can compare the baseline undisrupted condition with the disrupted condition. So we can calculate the total delay across the whole system for all journeys between all origins and destinations, and multiply this by the number of people making those journeys from the census journey to work data. So we can calculate a person-minute delay, the total delay to the system from one of these events in terms of transport delayed on the network. Once we've got that person-minute delay, we can then intersect it in different ways. So if we think about a destination, if we sum the delays at a destination, we get the total disruption to businesses who are located at the destination. So all the journeys that are traveling into that location are disrupted and delayed by a certain amount, and we can calculate the disruption at the destination end. We can also do this from the origin. So we can sum across an origin, and then we get the disruption to the residents who live in a particular location. So by doing that, we could find which locations are more adversely affected and understand whether it's the areas of the city with poorer residents that are more likely to be disrupted by these kinds of flood events, or areas with more affluent people, and we can understand the inequality effects of that too. So what we've done here is summed this at the destination end. So this is the City of London zone, the orange zone I showed earlier. Here are the number of jobs in the finance sector in that zone from the business inquiry data. And here are the proportion of people who commute each day to that job. So we can calculate the person-minute delay across all of those journeys and sum that up. So we get 12 million person minutes is the delay from that 1 in 200 year flood event that I showed earlier. And that is a proportion of an economic output of around 12%. If we look at the daily output, we divide the GVA for that finance sector by 365, or however many work days there are in the year, we can then work out what proportion of economic output is reduced by that delay to commuters. We can also then calculate that in economic terms. So we can calculate that is for a one-day event for the finance sector in the City of London only is about £9 million of lost economic activity. Now, there's a big assumption here that all the people who were traveling into work didn't make it to work or weren't able to work during that time that they were delayed. They may arrive later, and the assumption is that that time is lost. Now, clearly, some people might stay and work later to make up the time, or some people might work from home, but that's another step in the model that we need to think about. And what we can then do is then sum this across all economic sectors in London, and we can calculate total economic costs for a flood event like the one I simulated, purely in terms of delays to commuters getting to work because of that flooding on the transport networks. And that sums to about 165 million for a one-day flood event in terms of delays. So just to summarize, I hope I haven't overstepped my 10 minutes too much. What we're trying to do is find a method to quantify economic impact of disruption to urban transport. And in London, we've shown how we might do this by linking together a number of models for a given simulated flood event. Now, clearly, there's a lot of assumptions in this model and a lot more steps that could be taken, but it's a step at building this framework to get us from rainfall event to indirect impacts. As I said, summing at the destination gives us the business impact, so we can identify key economic locations that are disrupted, or we can identify key transport links that need to be protected to maintain economic performance. If we sum at the origin, we can get the residential impact, identifying locations where vulnerable populations may be at risk from disruption to their journeys to work. Outputs like this could be fed into an input-output economic model to quantify further second-order cascading effects through the economy as well, from sectors that rely on the sectors that are disrupted in this part of the process. Okay, so there's some papers I referenced during the talk, and thank you for your time. That's my presentation.
Okay, many thanks, Alistair, for your interesting presentation. And now is the time for the presentation from Eduardo Martinez. Eduardo holds a PhD in civil engineering obtained at the University Polytechnica of Catalonia. He has 15 years of experience in water-related projects, and currently he holds the position of Research and Development Project Manager at CETACUA. He has been involved in the management and development of urban resilience related European funded projects such as Pearl, Bingo, Rescue. Moreover, Eduardo teaches hydraulics to undergraduates at the University Politècnica of Catalonia. We are going to see now a presentation which is very, very interesting for me because I work a lot on this issue in the past. The title is Pluvial Flood Damage Model and Applied to Barcelona Case Study. The floor is yours, Eduardo.
Many thanks, Pere, for the introduction. And good morning, everybody. Following, I will present a piece of research conducted within the framework of the European Union funded RESCUE project. In particular, this presentation will be focused on the development of a tool to assess flood damages to properties and its application in Barcelona. Well, a great variety of models have been developed in the lifetime of this project, and not just to assess risks due to flooding, but also others such as droughts and CSO spills into coastal bathing areas. In this presentation, as I said before, I will explain just the model that we have developed to assess direct damages to property when an urban flood occurs, and its application to Barcelona. Pluvial floods may not be so devastating as fluvial ones, but if we aggregate flood damages during a period of time, both are equally damaging. Barcelona, for instance, suffers from pluvial floods, and is the third municipality in Spain in terms of flood damage to properties, as you can see here in this graph. The most valuable data to validate flood damage assessment models are insurance data. In Spain, the public insurance company Consorcio de Compensación de Seguros is responsible for the compensation to policyholders after a so-called extraordinary risk occurs. Among these are, for example, flooding events, and we can distinguish between two relevant data: the surveyor appraisal and the final payout. The first is the closest value to the actual damage, and the second is the amount of money that policyholders finally receive. This difference is mainly because of the deductible and the insurance related to the policies. It also has to be into account that the difference between the surveyor appraisal and the actual damage depends on the insurance penetration level. In this graph here, you can see both insurance type, both insurance type of data for the period 2009 to 2019. Also, in 2011, 2018, and 2019 those years have been the most damaging years in Barcelona, as you can see here in these graphs. Okay. Well, these are the three selected events to test the flood damage model. In the upper row, you see the volume of rainfall distribution across the across the city, and in the lower row, you see their corresponding related damages to property. It is worthy to highlight how important is the rainfall pattern in the damages cost. For instance, the second event, the one in August 2018, produced a maximum volume of rain of 75 millimeters with a duration of 2 hours and 40 minutes. And its related damages were around €500,000. However, just a bit more of rain volume and even less duration cost more than €4 million in the last event in September 2018. It has to be observed that during the first rainfall event, the maximum amount of water fell along the low-lying area of the city, unlike the second one that was more evenly distributed across the city. Flood insurance surveyors are the ones who first apprise the flood impact by providing a preliminary flood damage estimation to the public insurance company, the Consorcio de Compensación de Seguros, as I said before. This estimate is valuable for the consortio in order to set aside the required amount of money for the compensations. According to conversations with the consortio, these estimates tend to be very accurate. This means that insurance surveyors are the most expert to assess flood damages. Based on this, we have tried to gather the know-how of an insurance surveyor into a toolkit. And in fact, this person, this surveyor, has collaborated with us all along the tool development process. Without entering into the details, this is the conceptual model proposed based on the advices of the insurance surveyor. As you can see here, 6 types of building layouts were considered, with only ground floor, with ground floor and 1 basement, and also 2 basements. Besides, those levels can either be a car park or not. Water depths are expected to be higher on the streets than inside the ground floor. Also, a maximum water depth is proposed in the layouts with 1 or more basements, since the water flow from ground floor to lower levels is expected to occur through stairs or lifts, which would act as weirs. Once the maximum water depth is reached, water is steadily flowing down the lower levels. And a maximum water depth is proposed too, since once the process ends, a certain amount of water is retained in those floors with existing lower levels. Well, in order to apply the conceptual model, a couple of, let's say, sub-tools were developed too. The permeability coefficient was proposed first. It is the ratio between the water depth outside and the depth expected inside the building. Since this coefficient is expected to vary with the water depth outside, relationships between depths outside and permeability coefficients were estimated according to the surveyor suggestions. On the other hand, since large floor areas will not be entirely flooded, unlike small ones, relationships between the expected flooded area and the total flow area, and the total floor area were proposed too. As a key element of flood damage models, tailored depth damage curves for Barcelona were derived according to the insurance surveyor suggestions. As you can see here in this graph, 14 types of property uses were considered. Once the water level is established in each building floor, it can be related to its corresponding curve to obtain the flood damage cost estimate per square meter. The tool has been implemented in a GIS environment, and the workflow is depicted here. The required input data is, on the first hand, cadastral information, which is freely downloadable from the Spanish cadastre website. On the other hand, the flat map, which should be a shapefile, must be provided to. Currently, the tool contains a database of depth damage curves for most of the Spanish municipalities. Therefore, the user only has to select the municipality to be studied and just run the tool. And also the tool will provide not only a map with the computed damages, but also a file with a summary of the results. Well, following, I will show you the results after applying the tool for some different actual flood events. This is the case of the flood event occurred in 2011. The first thing to analyze was the damage distribution. This graph presents in the horizontal axis the census districts of Barcelona versus the damages within them. The dashed line in this graph is the best fit of computed damages, and the continuous black line is the insurer surveyor appraisal. Since different parameters are involved in this methodology, well, a calibration process was conducted, being as I said, the dashed line the best fit. Here you can see the damage map where the different parcels damaged according to the model, of course, are highlighted in red. Okay, you can see here all these the red parcels. In this other map, you can see the census districts that received compensation from the Spanish Public Insurance Company. What we can also see is a great correspondence of the flood extent and the damaged parcels. It means that the response of the hydrodynamic model was accurate and represented well the flood extent. It has to be noted here that the hydrodynamic model for the drainage of the city of Barcelona was developed by the municipal company Becasa for its acronym in Spanish, responsible for the water cycle management in the municipality. Well, the calibration and validation of this hydrodynamic model was conducted by other means different from the overlapping of flood extent and payouts distribution. The assessment of this other event did not produce accurate results. The computed damages were much lower than the compensations, as it can be observed here in this graph. The dashed line, the computed, does not fit at all with the continuous line, which are the payouts. This is what you see here is the output of the damage model for this event. That shows parcels in red, across the flood extent. Just a few parcels can be spotted over here in this image. In this map, the hydrodynamic output flood extent is overlapped with the census district that receive compensations. It can be observed how the flood extent does not fit well with the actual census districts damaged. The damage model accuracy is highly dependent on the flood extent, and therefore on the hydrodynamic model output. These are the aggregated figures related to the appraisal, the payouts, and the computed damages for the 3 flood events. I just show you a couple of them, the best and the worst. While the results for both of them can be considered accurate enough, the third must be discarded. The model outcomes can be considered as accurate, not only focusing on the aggregated damages.
Please, Eduardo, Pere Malgrat, you need to
speed up. I know. Just 1 minute more, please. Sorry. The next slide are the take-home messages.
Thank you.
Thank you. The model outcomes, well, can be considered as accurate, not only focusing, as I said, on the aggregated damage estimate, but also in the damage distribution. Well, just to conclude, let me list some take-home messages. The first would be that pluvial floods are very relevant from the economic impact point of view. Although a single event may not be, as I said at the very beginning of the presentation, devastating, their high frequency of occurrence causes remarkable aggregated economic damages. Besides, not only those cities in the vicinity of the rivers are expected to be hit by pluvial floods, but all of them. Also, insurance industry are a key ally to assess flood damages, and well, in this case, their collaboration has been paramount. With this tool, what I can say is that we can assess pluvial flood damages in any municipality nationwide, and it could be useful to contribute to future EU floods directive updates. And that's it from my side. Many thanks for listening, and I'll be happy to answer your questions, if any, at the end of the session. Thank you.
Okay. Okay, many thanks, Eduardo. Now is the time for the third presentation. The speaker will be Darío Redolat. Darío studied geography and spatial planning at the Complutense University of Madrid. He's a meteorologist by the University of Barcelona and is currently a PhD candidate in physics focused on seasonal forecasting and global teleconnections by the Complutense University of Madrid. The presentation will be about reliability and usability of multimodal projections to analyze climate impacts in urban areas. Please, Darío, it's your time.
Okay, thank you, Pere. Good morning, everybody. Let's start with my presentation. Okay. Good morning, everybody. I'm going to review the work what Climate Resist Foundation has done through the last 4 years in the RESCCUE project. First of all, we can start with the reliability and usability of this tool. Firstly, for a proper use of this predictive tool we offer, we need to know which variable or variables interest to us. Temperature and precipitation, just wind, just wave height. On the other hand, how these variables affect our sector due to climate change. For example, we will have more heat waves, greater risk to the infrastructure, to our plantation or farmers, etc. It's very important that this information be readable and understandable. So we must also provide other details, such as the location or the referencing, the duration of the phenomenon, we want to know the changes in a short or a long term, in other words, the anticipation of the phenomenon we want to know. And in addition, the characteristics of use will be needed, whether we require weather forecasts or climate projections, how many models we use, how many RCP scenarios are employed, if we need a downscaling tool to work on smaller geographical scales, a municipality, a port, etc. Once we have this question resolved, what should we do? We also need to collect other information, okay, as historical references to have precedents that can help us to understand possible risks, obtain the event variables, to identify thresholds for each variable, estimate the impacts similarly on our sector. And besides, depending on what we want to know, we'll use different tools. Okay, for example, for an hourly forecast, we'll use a deterministic weather forecast. Okay, for time of the next week, we'll use a probabilistic weather forecast. For forecasts or climate in the middle of the late century, we'll use an ensemble climatic projection, but never will use a deterministic climate projection, right? Okay, let's see some examples of the data and methodology. Here we have table 1, the example of global models using the derived correct method. Okay, for dynamical method. To achieve the reliability in the climate projections, it's required to use multi-model ensemble strategy. And in the RESCCUE project, we mainly use a set of Earth system models collected from the CMIP5 coupled model intercomparison project, phase 5, from the to support the IPCC. Okay. And these climate outputs were done scale by using observed time series. Concerning this dynamical method deeply, we can see, we can say that the climate extreme events present a higher error than the average climate projections. For this reason, it was applied a quantity mapping of the return period values compared with the observations. Okay. Additionally, to improve the usability of the results, the uncertainty was summarized, and we sorted the climate projections and 3 representatives. Okay, 3 representatives, percentiles 10, 50, and 90% were represented by KML polygons. Okay. To condense the statistical methodology, we can condense it as the hypothesis of the atmospheric system as a set of perturbations, okay, which can be obtained through a harmonic function based on teleconnections for limited climate and seasonal forecast. In the table 2, you can see some indexes that the variables considered as these indexes can be seen surface temperatures, sea level pressure, rainfall, among others. So to summarize both methods, we can say that the reliability of the results was increased by comparing with the dynamical outputs from CMIP5 climate projections and climate forecast system, respectively. Okay, that was intense. We're going to see some examples of validation of extreme events. Okay, in the table 3, you can see the number of simulations which pass the validation test for the dynamical modes-based method. Okay, in the rows, you can see the variables, methodological and hydrological variables we used. In the columns, the pilot cities of the project, of the RESCCUE project, and also the projections and the characteristics for each type of variable. In the figure 2, you can see an example of the climate projection of extreme indices for Lisbon city based on temperature. You can see a short decrease of cold days and an increase of both warm days and tropical nights along this century. And for the figure 3, a projection of extremities based on summer starting day, you can see the advance of the beginning and the increase of the duration. And similarly, for the duration of the warmest period of the year. In figure 4 is a string compass rose for Barcelona, which gives an idea of the evolution of the meteorological variables along the century in the city of Barcelona. As can be seen, you can see the variables that experience the greatest increase will be the heat wave days, the extreme temperature, and the drop. The center of the rows represents a null change percentage, and the line of the edge represents a change of 100%. So, to conclude, we can confirm that in order to generate climate scenarios, high level of local, regional detail is necessary in order to the predictions be as accurate as possible. It's not recommended to use a single prediction to forecast the future, but an ensemble of predictions to better estimate it, and adapt it every particular situation for each user, so that all variables are understandable and according to the requirements of each user. So that's it. Thank you for your attention. Questions later, no?
Yes.
Okay.
Okay. Thank you very much.
Thank you, Pere.
One moment. Thank you very much, Darío. Now is the time for the last presentation. The last presentation, the speaker will be Dr. James Weber, who is a research and impact fellow working at the Center for Water Systems in the University of Exeter. James' research specializes in evaluating flood risk and resilience, and in particular focuses on the emerging challenges of surface water, pluvial flooding. Okay, James, the floor is yours.
Thank you very much, Pere. Good afternoon, everybody. Just share my screen there. Okay, so today I'm just going to be talking about a project that we've been working on as part of RESCCUE, where we've been working with some partners in Bristol, which is a city in the UK, and we've been looking at the different types of flood risk and how we can mitigate that flood risk using property level protection. So for those of you who don't know where Bristol is, there's just a little map of it there. Bristol is in southwest England, so it's just marked here on the map. And it's an area which has received sort of a couple of major floods over the past years. So in particular, it suffers from a range of different flood hazards. So it suffers from fluvial flooding from the River Avon and its associated watercourses. And in particular, in July 1968, there was a significant flood event where 7 people died in the city. It's also a fairly unique situation where it exists on the Severn estuary, and this can rise up and create a sort of storm surge situation, which can disrupt the existing drainage, but also increase the damage from fluvial flooding. And also the pluvial flood risk in the city is very significant, and it exists as one of the top 10 surface water risk areas in the UK at the moment, with over 22,000 homes at risk. So we worked with our stakeholders and we thought about how we can mitigate these risks. So we applied a sort of three-stage process to do this. The first stage was screening flood hazards, and we used existing modelling, which had been undertaken by consultants and by our partners. So we looked at fluvial flooding, we looked at pluvial flooding. We then designed some strategic flood interventions, and this was a very sort of preliminary analysis, so it's a fairly strategic high-level design. And we applied those at different locations around the catchment, and then we applied some damage assessment tools to look at the sort of the direct economic damage that we could avoid with those interventions. So the flood scenarios we're interested in, we looked at two main scenarios. We looked at a baseline scenario, which was current land use in the catchment with the current climate. We also looked at a sort of relatively extreme business as usual plus climate change scenario for the year 2115. And we did this both for fluvial flooding and pluvial flooding, and we looked at a range of different return periods. They're all just listed in this table here. The first step really was evaluating the land use distribution in the city. So this graph here shows a cutout of the city centre, and it shows the distribution of different land uses. So as you can see, the majority of the land on the sort of around the outside of the study area is residential. And then there's a watercourse that travels through the middle of the city here. And the land use around this is much more mixed with a lot of public buildings and warehouses and retail. And for those of you who've been to Bristol, this is sort of the city centre where there's a lot of the entertainment and other things happening as well. So it's quite a complicated environment. And we associated a flood damage cost curve to each of these land use types. And what this does is it relates the depth of water to a damage cost, and we have a curve for each type of building. So to start with, we looked at the fluvial flood damage distribution and the pluvial flood damage distribution, and we evaluated the 1 in 20 year floods for both of these. So as you can see, the fluvial flood damage is, as you'd expect, very focused around this channel in the centre of the city. And then the pluvial flood damage is a much more distributed hazard. So it's much more complicated to manage spatially. So we devised a range of different targeting strategies at a very high level to understand what we could do to mitigate this hazard. And we applied property level protection, and I'll discuss in a second how we represented that. And we used two different strategies to target our flood management interventions. The first was using what we called a priority zone. And this is essentially the super output areas, which is just a geographical distribution which splits up regions in the UK. And we looked at the flood damage in this area. So we picked out the three areas which were the sort of highest risk in the city. We did this for fluvial and pluvial flooding. And we also looked at individual properties, and we looked at those individual properties which had the highest flood damage associated with them, and we targeted those. And what we found is that for the fluvial areas, we had 235 residential properties in these three fluvial zones, and we had 339 in the three pluvial priority zones. And what we did is we wanted to be able to use the existing model, which had been done to a very high standard by the consultants we were working with, but be able to quickly assess the effect of these different targeting strategies. So what we did is we wanted to be able to use that existing model, the existing modeling. So we instead adjusted the damage cost curves for residential properties. This allowed us to make use of what was there and essentially adapt the cost curve to reduce the damage below a certain point. So here we applied property level protection, which is this sort of, it's a guard that you can put on the outside of a property. And we know from the literature that this guard is effective at up to about 0.6 meters. So therefore we were able to affect the damage cost below this depth. We found that we then investigated how how these different targeting strategies affected the total flood depth for the cities. So here we have the baseline and the business as usual with climate change cost curves. This is a curve which represents the sort of the distribution across a range of events. And we found that in the baseline scenario, there was approximately 0.7 million from fluvial flood damage. But this this is likely to rise very significantly to of almost 12 million in 2115. And this is predominantly due to the tide locking, increasing the fluvial flooding. And if we sort of break this down a little bit by building type, what we found is that the interventions didn't seem to have a significant effect on this flood damage. And this is mostly because of the area affected by this type of flooding isn't really the residential properties that we were targeting. It was mostly quite a mixed range of properties. Therefore, although the interventions we were applying were benefiting the catchment and were making a difference to the flood damages, these weren't really reflected in the total values. So we'll look at this in a little bit more detail in a second. We did the same thing for pluvial flooding. And what we found is actually in the current day situation, pluvial flooding is a significant risk and is potentially going to cause more flood damage than fluvial flooding. And that sort of echoes the importance of pluvial flooding from the presenters earlier in this session. This risk is forecast to worsen in the future, but not quite to the extent of fluvial flooding. So in the future, fluvial tidal combined flooding is likely to cause significantly more damage in Bristol. And again, if we break this down, we actually find that our interventions have a much more significant impact. And this is because the majority of the areas affected by pluvial flooding is actually residential properties, as you can see from these graphs. And I think this is a really important point in terms of how we're defending about different floods, because different floods are going to have very different impacts to a range of different types of buildings, and pluvial flooding is often very difficult to predict and often does affect residential properties. So if we break down the effectiveness of the property level protection per installation, what this graph shows is the average effectiveness per installation in a residential property in our study area. The blue bars show the pluvial flood benefit. So the benefit is the avoided damage, and the orange bars show the fluvial benefit. If we look at the baseline scenario, we can see that the fluvial benefit is not large, and the pluvial benefit is much higher. And we can also see that the benefit of applying an individually targeted strategy for the pluvial flooding is significantly higher than this zonal strategy. So this really supports the idea of applying high resolution flood modeling when we're targeting pluvial flood defenses. If we look at the climate change scenario for 2115, we can see that actually we're getting higher benefits for installation of each measure. So this is good. This shows that we're defending more of the hazard. And we can see that we also get a much higher degree of protection from fluvial as well. So more fluvial flooding is likely to affect more properties, but we can respond to that. And what we could see here is that, again, this individually targeted strategies perform better, but that difference isn't so big for fluvial flooding. So this supports a zonal approach for that. And then sort of one last point to say is that we also looked at the number of properties which were flooded. What we found is that we don't always necessarily protect the highest number of properties if we just select those which are the most damaged. However, this method doesn't necessarily reflect those homes that we save during smaller events. So I think it's really important at this point to say that it's very crucial that we consider which metrics we use and which design storms we use for analysis. So thank you very much. Happy to take any questions in the panel chat later. Yeah, thank you very much.
Okay, Many thanks, James. Now is the time for the questions. It seems that we don't have at the moment questions from the public. Maybe I could try to do some general questions for the 4 speakers or for some of the speakers. In any case, many case for all of you. Maybe one question that we can do is we have seen a lot of interesting studies of damages, direct, indirect, and so on. But they are studies. In some way, the difficulty is if you need to take decisions in a city like London or like Bristol. Do you think at the moment, let's say, the policies of the cities are prepared to work with all these data? I mean, finally, one thing is to have data of 1 year, but when you need to take decisions for the future to avoid floodings, you need to establish policies and to say, I want to protect, for example, Bristol or London next 100 years in this way. And to take the decisions, you need data, and a lot of times you only have data of 3 months, 1 year, very limited data. What do you think about that?
I can try to answer that, Pere. I think there are lots of different types of data that cities need. I mean, one of the problems that we had doing the study in London is the lack of meteorological data, the lack of representative weather stations across such a big area, and as Eduardo showed in his presentation in Barcelona, you know, the variation of extreme rainfall during one of these kind of storm events that causes the type of pluvial flooding we're thinking about is very spatially variant. So we need much better data on the actual rainfall intensities. We also, we try to simulate the pluvial flooding using, we used a 4-meter DEM across the whole of Greater London. Well, clearly a 4-meter DEM averages out a lot of the topographic detail that's present in a city. So we need very detailed DEMs, and we need representations of the urban drainage network to capture that pluvial flood risk itself, the hazard. But then we also need data about, in our case, when we're thinking about the transportation system, we need data about users on that system. So we're currently working on a project called Flood Prepared, which is trying to use CCTV images and traffic sensors to build a much more realistic representation of the use of those road networks. So we can couple all of these parts together. We're using rainfall radar for the pluvial flood, for the extreme rainfall representation. But I think it's a very complex picture, and it requires a lot of data and a lot of modeling power to be able to better understand what the true risk is from these hazards. But I think we have to do it, because if we want to capture the genuine risk of the increasing extreme rainfall because of climate change, we need to try and build these frameworks and systems that we've seen in all the presentations in this session today.
Okay. Many thanks. I don't know, maybe another question that we can't find is or in all the four things in the 4 conference, we have seen a lot of studies referring to floodings, okay? But urban drainage systems need to avoid floodings, but also need to avoid, for example, CSO or environmental impact to receiving waters. No? And in fact, I'm the representative of the Spanish Association of Water Supply and Wastewater Companies in Euro, in the European Association, and we discuss a lot about that in a way that we only have one urban drainage system. Of course, we need to, but also we need to avoid, for example, CSO. We also need to take decision to rehabilitate the sewer system. In some way, we need a more holistic approach. But I appreciate in all the world, we only can have a few examples where people really work in an appropriate way in this holistic way. And I mean, people try only to concentrate in one of the problems, but finally, for example, you can have, you need, for example, to build a detention tank to avoid floodings. This detention tank also can collaborate to have less environmental impact of a CSO in Thames River or in other, or in a beach, for example. No? So, what do you think about that? Do you think cities are prepared? I see a lot of times we can have problems of competence. For example, I remember the case of Bristol. The people who manage for example, the council manage, let's say, urban floodings, but CSO are managed by the Western water, for example, this kind of things. No, we can have difficulties because different competence referring to the issue. But finally, we need to think in a holistic way. What do you think about that?
I can just say a couple of things on that if you like. So I totally agree with you. I think one of the biggest challenges we face in drainage design and managing cities in general is actually how we can design infrastructure to be as holistic as possible and to encompass, I would say, there's a whole range of sort of multiple benefits we should be thinking about as well. So I don't really have the answers to that, but I think as well as I very much agree with what you're saying, that it's very important to consider CSOs and water quality alongside flooding. But I think the other challenges we need to think about is how we can design infrastructure which also responds to those other issues that we face in cities. So heat islands and biodiversity and recreational space, and also just creating environments that people enjoy living in and are sort of physically and mentally healthy. So I definitely agree. We need to think holistically, and I think there's a range of interventions and strategies now, which hopefully will start addressing lots of different challenges, and also hopefully integrate and maybe even save money by having different organizations who are responsible for different parts of these challenges working together as well.
Okay. Many thanks, James.
Can I just respond to James? I mean, I think that's a crucial point, that quite often we see all different parts of the same organization even working in silos. So you might see something like Bristol City Council or the Greater London Authority. You know, there's the transport people who think about transport, and then there's the environment people who think about green space and the environment. Then there's probably the flooding people who will be in a separate office. And I think it's crucial that we think of cities as systems, and we have that overview of how all of these parts interact and influence each other. So we've been thinking on the transport network, the adaptation options, you know, traditionally are bigger gullies or more water capacity to take the water off the roads, but clearly with more and more extreme rainfall events, that is not going to be a sustainable approach. So we've been thinking about how we protect the road network, not on the road network, but in locations that are distant spatially from the road network. So you can kind of trace back through the water flow paths and find somewhere you could put a flood retention pond that could hold that water back. So, or you could also think about how you adapt the transport network by early warning systems, so that you give people warnings when there might be extreme rainfall, so that you don't see the levels of impact that you might have if people all get in their cars and go to drive home when a storm happens. So we have to think about this systemically and think across a number of sectors, not just about flooding and water management in isolation.
Okay. In fact, a particular, let's say, a particular problem of this lack of holistic view is about, let's say, river floodings and urban drainage flooding. As you know, the Floodings European Directive mainly it is focused in river floodings, flash flood, and coastal floodings, but not in urban drainage flooding, not an obligation, let's say. So it's not the case, I know, in Bristol, but I see in a lot of cities, let's say there are two silos, the silo of the river floodings and the silo of the urban drainage flooding. And there is no good connection between them, but really, well, in UK, you know very well, there is a relation. A lot of times you have both and you need to deal with both. So I think it was a big error of Flooding European Directive not to put as obligation to include also urban drainage floodings as one of the floodings to study in a city. Do you think it's a limitation? Because I can appreciate that because of European Flooding Directive, we see a lot of, let's say, national studies of rivers and so on, but probably the level of urban drainage studies is not the same because this lack of obligation in the European Directive. What do you think about that?
Well, may I think, well, I totally agree with you. It should be an obligation, definitely, in Spain. But I would say that the main barrier here, let's say, is that the complexity of the models, let's say, that we have to use to analyze floods for urban areas, those pluvial floods. I mean, for instance, in Spain, we have some free, we are using Iber or Iber, which is a software free for free use. But when it comes to software related to urban drainage, we have to pay a lot for the licenses, for instance. I mean, I guess this is one of the main barrier here in Spain, that we decided to start for riverine floods at the very beginning because it was easier to analyze these flood impacts. But to be honest, I think that currently we have the tools, the needed tools to analyze also the pluvial floods in urban areas. As I showed you before, we have even tools to estimate floods, to estimate damages caused for pluvial floods in urban areas. So I think it's imperative that in the next European Floods Directive, they should not recommend, but it should be mandatory for all the state members to take into account also pluvial floods.
Okay, many thanks, Eduardo. Just I would like to remark that nowadays it's the European Commission is in the phase of deciding about the revision of Directives 91/271 about treatment of wastewater systems in Europe. And they are discussing now with the main stakeholders several policy options. And one of the policy options is to promote an integrated planning of urban drainage system and wastewater treatment plant. So maybe it could be a way to boost this analysis more holistic, because if you analyze urban drainage water treatment plant, of course you need to take into account the flooding problem. In fact, in Spain, in a draft regulation that we are making now in this month, we are proposing this kind of things. No, well, thank you very much, Eduardo. I have a question about. It's a question for James. It's about. It's for Bristol. The question is: which adaptation options for infrastructure are in the Bristol agenda? It came from the public.
Hi there. Yeah, thanks very much for the question. So I don't know exactly which adaptation options Bristol are considering across their whole sort of investment. To be honest, I think that they would be considering every option available to them for the different types of flooding. The specific study that we looked at together was specifically focused on the potential for property level protection. But I know that the people we were working with across the stakeholders and across the council have got other studies where they're looking at other different types of defences as well. So I think that they would be considering everything from green infrastructure and sort of water sensitive urban design through to sort of more conventional pipe upgrades and things like that as well. So yeah, sorry if I can't be a bit more precise on that.
Okay, many thanks, James. I don't know. I don't see more questions from the public. Maybe a question for Darío. About climate change, still I appreciate that let's say cities and countries have difficulties, let's say, to use in a global, in a practical way, let's say, all this kind of analysis as you shown us about the scenario and so on. I mean, it's true that I know that, for example, in Denmark, nowadays, to plan the measure against flooding, they have changed the rainfall design with climate change in order to decide the actions in all the countries. But still, I appreciate it's not very common, let's say, at national or in a local level. What do you think about that? Do you think still we need more time and more let's say more good methodologies to implement in a practical way? What is the difficulty for cities or countries to implement in a practical way? Well, it's for Darío, for everyone.
Okay, yeah. I can answer the question, I think. Well, I think we need to translate the climate risk information to needs the end user. That's doesn't make with other variables, as I said before. I think that all this question should be translated to the other to the governments, not just to the local municipalities and local regional governments, because they use non-specialty tools, but the governments, the national governments, should use that derivate variables we offer, and we need to provide summaries of the results with with new maps, with new studies, with these tools, etc. I think.
Okay, many thanks, Darío. Well, I think it's quite okay. We have discussed a lot about many things. Maybe it's the time to make some conclusions of the session. I think we have seen 4 very interesting conferences about the general issue of climate impact assessment. I think the interesting is that we have seen, let's say, methodologies, but also applications to real cases and, well, in fact, big cities like, for example, London, Barcelona, Bristol, no? Which is very interesting in order, let's say, to see how these methodologies can be used in real case and real data. In any case, my impression is that still we need some more time, let's say, first to have in the cities and let's say the governments the culture to take data of everything, of the infrastructure, of the performance infrastructure, of the rainfall, of the damages, especially in damages. We have a big lack of data. I remember when I make it was the master plan of Barcelona in 1988. We tried to get data about damages in the city. We make a big questionnaire to a lot of entities, and finally, only one of, let's say, 30 entities answer us with the damage of one pumping station in one railway station. It was really a disaster. I see that people don't have data. People, I mean, local government, regional government, railway companies, electricity company, and so on. Students nowadays, especially with the things of insurance and so on, things are changing, but still, I appreciate a lack of data in the cities. No, I think also in the future we need to make the change from to use all these methods and studies to policies. The real important thing is to decide good policies. One example that we have common of a bad policy is the European Flooding Directive. If we try to solve floodings and we don't put urban drainage system in the equation, we have a problem, because we try to solve problem in a city only taking on one part of the system. No? So policies are important, European directives, national directives are important, and let's say it's a challenge to use all these methodologies, all these results as we have discussed today in the policies to improve the things. Because finally, if we have floodings, we need to take decisions. We need to build, let's say, a detention tank, water and sewer, or a gate, or we can do a lot of things. But to design these things, we need good policies and take into account all these things that we have discussed today. And important to take into account damages, and important to take account not only direct damages but also indirect damages. And well, probably we can say more things, but I think they are the main ideas for this session. Thank you very much to the speaker, to the public to listen and to discuss all the things, and to the organization of the Congress for this session. Okay, thank you very much.
Thank you.
Thank you.
Thank you, everybody.
Thank you.